we have today. I'm Andrés Prada. I'm a computer vision machine learning based object recognition for autonomous driving given by Julia Nitsch. Welcome, Julia. Julia has studied information and computer engineering at the TU Graz, Austria. She received her master's in 2016 with a major in autonomous robotics. After her studies, she worked at the Robotics and Perception Group at the University of Zurich on urban research and rescue robotics. Since 2016, she is employed at Ibeo Automotive Systems GmbH and did her PhD studies in cooperation with the Autonomous Systems Lab from the ETH Zurich. Yeah, we'll just give you a... and the question is all yours. Thank you. Also, before you move in, I just wanted to encourage you all to write down your questions at any time in the chat, so I can just ask her later on. So here we go. Thank you, Julia, for being here.
Thank you for this warm welcome. I'm really happy to present my work here, and I think it's perfectly fitting to Boris' keynote interview. I'm just following up on this whole autonomous driving exploration and what we are doing in this field. So for those of you who haven't heard about Ibeo before, we are an automotive supplier located in Hamburg, Germany, and we are building solid-state LiDAR sensors. I guess LiDAR sensors is not well known in the community of data scientists. I'm just going to share a video where you can see or get a feeling of this data. When we are talking about autonomous driving, we are often talking about the highway use case in Germany. However, especially from the research perspective and maybe from other use cases, for me, the urban environment is really interesting. And what you can see here is the data which we get out of our solid-state LiDAR sensor, which is represented as point cloud. Point clouds are unordered lists of points. Just for clarification, we put here also an RGB image. And this is something which we call intensity image, which we also get out of our LiDAR sensor, which is simply a 2D representation of the intensity values. And as you can see in this data sample, we have here a broad range of road users, which we should detect and incorporate for our anticipatory driving style. As Boris already said, so we use the car as our data collector. And one of these cars, for example, is equipped with a multimodel setup. Multimodel means we have different sensor types because all of these sensors have strengths and weaknesses, and we simply want to sense the environment with all of them. Just examples are camera, of course, our LiDAR sensors and radar sensors. And this is how such an automotive solid-state LiDAR looks like. It's simply a box which you can then mount into your car. So this is really designed for being incorporated in the car design and not being like a bubble on the rooftop. This is the car, these are the sensors, how we collect our data. But what kind of data do we actually get? And there the first issue starts. We don't get the same data format for each of those sensors. So we have different data representations. As I already said, we have a point cloud, which is an unordered list. We also have 2D image representations, which have usually 3 channels for the colors. And we have something like this intensity images from our solid state sensor, which gives us information about the intensity values projected to 2D, or for example, the depth information. We collect this raw data, this is binary data, just to give you a feeling why this is such a huge amount of data. When we're talking about text files, we usually have for one page 13 kilobytes of data. For the point clouds, it's still fine to have it for one scene, but what really kills us are high resolution images, and we need to store them in this binary format because we cannot store them as an interpretable format, because then the memory would be blown up completely. And this binary data format, which we need in this automotive setup, is really a challenge for index-based search engines, because they can't open the data, look inside, and then get information out, because that would simply last too long and you would look forever. So what people try to do is starting with SQL tables, simply with attributes, so that they can look for the data they want to look. For example, like the recording date or label information. And this, like, getting the type of label which you need for the development is something like a never-ending story. So if you're asking like 5 developers, you get 20 different answers what they really need currently for the development. So this is something which we call, this is the eierlegende Wollmilchsau in German. So this was not possible to define beforehand, before the development started. What we are looking into is now something which is called object storage. And I will quickly explain what this nice storage, or the properties of this nice storage, and how it looks like from a user perspective. So we store our data now in buckets. Within these buckets, we can store any type of binary data which we want to have. So it doesn't matter if we're storing point cloud, image streams, or completely different data. And alongside this binary data, we are able to store human interpretable labels. And the most important thing is that we can stick different labels to different files. So this is the huge benefit compared to the SQL label storage, where you always need to fill the complete label type. Of course, we don't only have a single bucket, but we have multiple buckets, and this whole collection is sometimes called a data lake. With this data lake, we have the ability to store these binary files plus the labels. So we don't need to open these files when we are looking for something. We can simply look at the labels. These storage types are extendable to petabyte. So in the background, they are extendable. They have handlers for this. So this is one of the big benefits for automotive here. As I said, it is extendable. And the nice thing is that these data lakes usually have common interfaces. Yes, you can switch the backbone, but still stick to the same interface. And just one example of this interfaces is the S3 interface, which is kind of known maybe from the AWS S3 cloud. So this is about the storage itself and how can we extend it. And the nice thing for the user are really these labels. What can we do with the labels? We can transform this type of labels to index files, which then can be used by search engines, and you can really grab through or crawl through this index files and look for the labels you need and the files you need. And this is the big benefit from the user perspective of this setup. And just to give you a name of such a search engine, one example is here simply the Elasticsearch. You might have heard about it in the latest news, because it was also able to use it in AWS. Just a quick summary what we currently have. So we are able to store our files. We can add labels and look for these labels, or search through the labels. The big question is now, how do we generate these labels? And for this label generation, we want to use data-driven algorithms, or in particular machine learning, because this is, as Boris said, it's one of the most precise algorithms which we currently have, and we have huge possibilities here. And one example of such a machine learning approach is the semantic segmentation. Semantic segmentation means we assign a label to each single point in the point cloud. And this cannot be done with traditional algorithms blown up. So we use machine learning here. So what you see in this video is our machine learning model only operating on the point cloud. The image is just for the visualization for the video. We only work on the point cloud and single labels to all the things which we can see in this highway scenario. This is a German highway. So what do we see? We see the different lanes, the lane marking, trucks, cars, obviously, and we really can see how this is separated and really assigned for each of the single points. And we then have to look for the semantics in the point cloud. The other kind of obvious use case is object recognition. So obviously, we also want to recognize objects. As shown here, we have here cars, which we definitely want to detect because we want to have an anticipatory driving style and we definitely don't want to crash into them. And again, this RGB image is just for the visualization. What we can do is using this intensity image for object recognition, it applies similar algorithms like on a traditional computer vision basis. So you can see we are using this intensity image, but are still able to detect the cars as they appear in this intensity image from the LiDAR point cloud. This is just for the object recognition. We also have some other obvious use cases. So we need to detect the traffic signs, obviously, or the traffic lights. And therefore, we definitely need the camera or the RGB image to distinguish between the lights. This is all about the object recognition. And the third use case I want to talk about is object prediction or road user prediction. Why do we need this? So when we are driving with our ego vehicle in urban environment, we usually see pedestrians on the street. And pedestrians are kind of these nasty road users who have really a broad range of actions they can take. They can go left, right, and wherever they want, basically, but they can also jump onto the street. And we have to consider or predict at least what they could do to have this anticipatory driving style, which we also have as humans. For example, if they're close to the road boundary, to drive more cautious, or predict if they want to cross the zebra crossing here. Obviously, it's not only valid for pedestrians, but we also need to consider other road users and what actions they might want to take in this urban environment. And this is the obvious use case here for the anticipatory driving style. And what's really becoming interesting is when we have blind spots. So especially behind parking cars, we have to double check what could happen in this blind spot. Could a pedestrian be jumping out? What could happen? Do we have to be super cautious? These are more the research questions here, how to incorporate this knowledge inside the ego vehicle. From this use case presentation, the key takeaways for you are definitely on the data infrastructure. So we have a big benefit on this object storage for large binary files, and it's extendable because due to the backbone which it's using, and we can use index-based search engines to crawl through the labels, which is a huge benefit compared to other structures. From the ML use cases, we want to use data-driven algorithms to create these labels, and they are especially important in urban scenarios because they are much more cluttered than the highway. We need this semantic information about objects to form higher level labels like the scenarios or the cut-ins Boris was talking about before, so that we can also attach scenario labels to our data, which is then again required to double check if we manage to detect every necessary object inside various scenarios. And that's it actually with my teaser here for the presentation, and I'm more than happy to answer the questions.
Thank you very much, Julia, for your presentation. It was quite interesting. For me, it was very interesting. And I have some questions, but I see that the people here are starting to ask some questions. So I will just move directly to them, and then I'll ask, asking, how do you prepare your ground truth data?
Yeah, so for the learning algorithms, obviously we have to start somewhere because we have this chicken egg problem. So in the beginning, we really started to label manually or to use also external label services. And we have soon, or switched to our one of our products, which is in this reference sensor reference domain, which is giving us labels on the data which we might refine manually. But once you get something like already a clue for the object, this manual just changing, adding, adapting is much easier than starting from scratch, drawing objects in the point cloud.
There's a follow-up question, I think, that for LiDAR also. So I think that's answered, right?
Yeah, so for LiDAR, you definitely have to have this 3D environment, and it's much more time-consuming than image labeling. This is something I can really tell, working now for more than 5 years with the LiDAR, it's much more time-consuming.
Thank you. Then let me just fish more questions here. Sarah is asking, do you do some edge computing, or is the data processed in the cloud? Where do you process all of the data for these algorithms?
It depends on which algorithms. So for this offline processing labeling part, we process the data on the cloud. But of course, we call it online algorithms. These are these real-time algorithms which are running on the car. There is a board computer inside the car where they have to run these algorithms online. So it depends on the use case. But for this labeling part, we are using the cloud infrastructure.
Yeah, something that I was continuing this question is, so you retrieve all of the data from the LiDAR and you process them on the car itself, and then you provide a...
Yeah, so it depends, as I said, on the use case. If you are just going out for data collection, we are driving around manually, collecting the data, sending the data to our cloud, and then processing it. Okay,
then more questions from Jelavis. How do you use your sensor suits for prediction?
For prediction, the sensor suits or the algorithms, but probably more the algorithms then. So when we are talking about road users, what you can think of how this is working. And first, at the time frame 0, we are detecting objects. And over the time, we see these objects and we recognize that we already saw these objects. This is something we call tracking. Like, we know we saw that object before, we know how it behaved. And based on this tracked information which we have over time, we can start with the prediction what it will do. Of course, if we only see it for the first time in one frame, it's super hard to run for the prediction. But once you followed this object for some time, you can run for the prediction in the online case. In the offline case, this is this going forward in time and backward in time, what was Boris talking about. There we have the information of the objects like over the whole time, where we can track it and also predict it. And this is how we train these algorithms.
Okay. I think if you have any suggestion first, I think that question Jelav is asking from the other one.
Could you repeat the question?
I think that's a follow-up question regarding how to use sensors for prediction. I think that was kind of follow-up sensor fusion.
Depends a little bit also on the use case, but actually in automotive, the late fusion approach is more prominent. Late fusion means we are processing sensors on their own, and once we detect the objects, they are then fused. This has a lot to do with the history, how sensor development, how algorithm development happened in automotive, where especially in the German automotive domain, where you have all these suppliers, the supplier is delivering a single sensor to the OEM, like for the big players like BMW, Audi, etc. And they are fusing it in their car. They are really integrating it. And they need sensors and algorithms which are qualified to put it in their car. That's how this thing came up.
Okay, good. Sarah is asking another question. Which type of algorithms are you developing with this data? How much autonomy are you trying to achieve with these algorithms?
So it depends, again, a little bit on the department, what we are following. So I'm more in the pre-development, let's state it this way, not in a serious development. What we are using in terms of algorithms is really the machine learning algorithms, which we are currently thinking of for object detections, for semantic segmentation, like autoencoder architectures here, for example, for the predictions, also working with LSTMs. I think nothing too special once you're inside this domain. What level do we want to achieve? Definitely L3 plus. So really having the driver taking off the hands and having some response time once he or she needs to get back. So really talking about this first autonomy steps. But it's not only limited to really a car in a classical sense, but we are also talking about people mover applications, intralogistics, simply stuff where robots are driving around on their own.
Yeah, thank you. Then Prakash is asking, which cloud do you use? Which cloud?
Yeah, currently we are using our in-house cloud. So we're really working on a private cloud solution inside the company, and that's what we're currently using.
Jelavis is asking again, one more question. For self-driving cars, how many solid-state LiDAR are you going to need?
Yeah, so it depends on the use case. It depends on which level of autonomy we want to achieve. And usually you want to have something like a 360-degree field of view. And the sensors have from 11 degree to 120-degree field of view. So you can imagine how much or how many sensors you need for the vehicle, depending on the size, to get the surround view. And what it's really important in the autonomous driving, you really need a redundancy in modalities. So if you see this field of view with the LiDAR, you might also want to have the same field of view covered with a camera, with a radar, to be sure if one modality fails for whatever reason, you can still stick to another modality.
Okay. Thanks. Then I just want to remind you there are like 5 minutes left only for questions. So if you have more questions, just feel free to write them down in chat. And if not, I will just move on to my questions that I have a couple of because I found it very interesting. Regarding the data collection, so I thought that you said that it's a manual process. Like you collect the data while driving the vehicles, and then you supervise that the labels assigned via object tracking are correctly, or is it completely an unsupervised and autonomous process?
It should be completely unsupervised autonomous process, integrated with no manual correction. But obviously we have people who check the labels manually to ensure the quality, maybe to adopt single bounding boxes and double check that. So I think it's really a process and a way to go until we can remove the last person out of this.
So human in the loop is still a fact that you could get rid of, yeah.
Yes.
We would all love to do it, but still. Yeah, okay, I completely understand you. Then in the perception layer, how many classes do you aim to identify? I mean, for how many type of objects? Because you said something like you cannot identify, for example, pedestrians. But do you have like pedestrian as a class or an identified object? Because I assume there could be thousands of things that can run into the car in the middle of the street.
Yeah, so what we have is definitely a defined number of classes. And to be honest, it's not that much. Like we don't have all the ImageNet class labels in there. So it's not like this amount of labels. Luckily, inside, what's really interesting for the autonomous vehicle, it's a limited number of road users. I think just from the road user perspective, we get up to 20. Then we have this roadside infrastructure. So it's not too much on the classification part. But what we definitely need, and this is something we can't get rid of, is something we call out of distribution detection, which means objects which did not appear in your training data set, which you assume this is your in-distribution data, but simply objects you haven't seen before. So I just came across something like a beer bike called in German cities. it's simply like a tandem where people sit on and drink beer and drive around in the city. This is something I have never ever seen before. This would have never ended up in my training data, I'm pretty sure. So what do you do with those objects? Obviously, you don't want to crash into it, but still, if you use supervised classifiers, they give you not such a good answer on the classification label. So you really need to detect that you are not able to classify it and assign these unknown labels to it. And there, these supervised classifiers, this is the pitfall of them. You really need to incorporate techniques for this OOD detection.
Yeah, I guess you need to get some logic out of, depending on the object, that can become really weird movements. Yep. Like a bike drinking beer could be completely random. Yeah, of course. I have one more question regarding these type of algorithms, because what you're doing at Ibeo, it's just developing some algorithms for the use case for the LiDARs, if I get it right.
Yeah, so from the series perspective, yes, we are focusing there on the LiDAR and supply this LiDAR with the algorithms. But obviously in the pre-development, we are working with more modalities and sensor fusion techniques just to learn how to fuse, how to use this data. And we buy the sensor, like the hardware.
How, for example, the case that you showed us in the slide, in the previous slide, that one of the last was that you could recognize and just not to bump into a pedestrian. Do you think this would be a feasible future, a feasible scenario that could happen in the near future?
You mean seeing these algorithms applied, or I mean not in serious development? Like, I don't see like these autonomous cars driving completely autonomous in the cities soon. So this is definitely something, way to go. In this pre-development step, yes, we are applying it, but as you know, the industrialization step, especially in automotive industry, it's like a huge process of deployment, qualification. So this will simply take some more time.
Yeah, okay, thank you. We've reached the time, so it's 1:15. So thank you very much for your great talk that we had today and for answering all the questions that we had from the audience. So I just want to thank you all, the audience, as well, for taking the time to be here with us. And just wanted to remind you that the next event for the datalift number 5 will be on May 24th. I've just written the chat down, the link. So if you want to register already for the link for the event, you can do so. And I hope you're enjoying this new event overlay that we are using here, this new app, Open. And you can move now to the expo or to the networking. Thank you very much.